January 5th, 1943. The dark waters off Guadalcanal. Lieutenant Commander Red Cochran stood at his battle station aboard the cruiser USS Helena, watching 4 Japanese dive bombers pull away from their attack run. His fingers gripped the firing controls of the aft 5-inch battery. For 18 months, American gunners had fired desperately at aircraft like these, watching shells explode uselessly in empty sky while enemy planes escaped into the distance. On average, it required 2,500 rounds to bring down a single aircraft, sometimes as many as 10,000. But this morning, Cochran's guns were loaded with something different, shells marked with distinctive red bands. Experimental ammunition that the Navy had shipped to Helena just days earlier, with instructions so secret that even senior officers weren't told how they worked. 3 salvos. That's all Cochran fired. 3 brief bursts from his battery as the Valdive bombers climbed away across the Purd. Solomon Islands morning. The second salvo caught one of the aircraft perfectly. The shells exploded in mid-air, precisely 70 feet from their target, without ever touching it. The Japanese bomber disintegrated instantly, torn apart by fragments that seemed to materialize from nowhere. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Helena's crew watched in stunned silence. They had just witnessed the combat debut of a weapon that would fundamentally alter the mathematics of warfare. A device so revolutionary that its very existence was classified at the same level as the atomic bomb. So sophisticated that German engineers would later examine captured examples and conclude they must be elaborate fakes, because the technology they contained should not have been possible. The Americans called it the proximity fuse, and the story of how it came to exist begins not in the Pacific, but in a converted automobile garage in Silver Spring, Maryland, where in August 1940, a volatile physicist named Merle Tuve was tasked with solving what every major power had concluded was an impossible problem. The summer of 1940 found America watching Europe burn. France had fallen. Britain stood alone against the German onslaught. And across both theatres of the coming war, one tactical reality was becoming painfully clear. Modern aircraft had made conventional anti-aircraft defences obsolete. A Messerschmitt fighter travelled at 300 miles per hour. A Japanese Zero could manoeuvre through violent banks and dives that made targeting nearly impossible. Against such threats, anti-aircraft gunners faced mathematics that offered no solution. A time-fused shell required setting a mechanical clockwork device before firing. The gunner estimated the target's altitude, calculated how many seconds the shell would need to reach that height, set the fuse, accordingly, and fired. If the estimate was wrong by even half a second, the shell exploded harmlessly above or below the aircraft. If the target maneuvered after the shell was fired, all calculations became worthless. The result was that British and American naval forces were firing thousands of rounds to achieve single kills. At Pearl Harbor on December 7, 1941, American anti-aircraft batteries would fire so desperately and inaccurately that 48 civilian casualties in Honolulu would be caused not by Japanese bombs, but by American shells falling back to Earth unexploded or detonating on impact with the ground miles from their intended targets. The concept of a shell that could sense its own proximity to a target had been discussed for decades. Make a fuse smart enough to detect when it approached an aircraft, and it would detonate automatically at the optimal range. Simple in theory, impossible in practice. The Germans had explored the idea extensively, starting in 1930. Their engineers developed more than 30 different prototype designs, acoustic sensors that would trigger on engine noise, electrostatic detectors that would respond to the charged surfaces of aircraft, optical systems using photoelectric cells, radio-based designs similar to radar. By 1939, after nearly a decade of research and hundreds of test firings, German scientists reached a unanimous conclusion. The technical challenges were insurmountable. The miniaturization problem alone defied solution. Even the smallest vacuum tubes available, those used in hearing aids, were far too fragile to survive the violence of being fired from a gun. When a 5-inch naval shell leaves the barrel, It accelerates from 0 to 2,800 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity, 20,000 Gs, instantaneously. Every component inside the shell experiences crushing force equivalent to being struck by a sledgehammer moving at highway speed. And that's just the beginning. As the shell passes through the rifled grooves of the barrel, it begins spinning at 25,000 revolutions per minute to stabilize its flight. The centrifugal forces are enormous. Any vacuum tube, any electronic circuit, any battery would be pulverized into fragments. Even if components somehow survived firing, they would need to function perfectly during the brief seconds of flight time before reaching the target, operating in temperature extremes from minus 65 degrees Fahrenheit in Arctic conditions to plus 160 degrees in the tropics. Hitler's armaments ministry issued a directive in 1940, prioritizing only projects that could reach production within 6 months to support the coming invasion of the Soviet Union. Germany's proximity fuse programs were cancelled. The British had reached further. Researchers at the Favre Telecommunications Research Establishment had conceived of using a small Doppler radar system. They built prototypes and tested them on unrotated projectiles, the British term for solid-fueled rockets. Rockets offered one crucial advantage over gun-fired shells. They accelerated gradually rather than instantaneously, subjecting their electronics to far gentler forces. British prototypes achieved success rates approaching 50% under ideal conditions. But Britain's industrial capacity was stretched to breaking. The cost of manufacturing even limited quantities of proximity fuses exceeded what their economy could bear, and the rockets themselves had serious limitations as anti-aircraft weapons. They were slower than conventional shells, less accurate, and carried smaller warheads. For military use against fast-moving aircraft, 50% reliability was inadequate. 10% of shells were already failing to detonate due to mechanical fuse malfunctions. A weapon that functioned only half the time would be worse than useless. It would waste ammunition, reveal the technology to the enemy through captured duds, and fail at the crucial moment when a ship or installation desperately needed protection. In September 1940, the Tizard mission arrived in America, carrying Britain's most closely guarded military secrets. Named for physicist Sir Henry Tizard, the delegation brought cavity magnetron designs that would revolutionize radar, details of jet engine development, and the complete research from Britain's proximity fuse program. American military officials examined the British work with deep skepticism. If German and British engineers, working for years with substantial resources, had failed to create a workable proximity fuse, why should American scientists expect different results? The answer came from an unexpected source. Dr. Merle Tuve, a 40-year-old physicist at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, examined the British research with entirely different eyes. Tuve had built his reputation studying the ionosphere, using radio signals to probe the upper atmosphere. He understood radio propagation, electromagnetic theory, and the mathematical principles governing wave reflection. When he looked at the British proximity fuse designs, he saw not insurmountable technical obstacles, but engineering problems that could be solved through systematic application of American industrial capacity. On August 24, 1940, Vannevar Bush, chairman of the newly formed National Defense Research Committee, appointed Tuve to head Section T, a classified research group tasked with developing a proximity fuse for naval anti-aircraft guns. Bush chose Tuve specifically for his combination of theoretical brilliance and practical engineering sense. The physicist had a reputation for being short-tempered, demanding, and absolutely unwilling to accept conventional wisdom about what was possible. He would need all those qualities. The task before him defied every expert opinion. Create a miniature radio transmitter and receiver small enough to fit inside a shell's nose cone, make it rugged enough to survive 20,000 Gs of acceleration and 25,000 RPM of spin. Add a power source that could activate under those conditions and provide electricity for the few seconds of flight time. Include safety mechanisms to prevent premature detonation. and do all of this cheaply enough that the Fuzes could be manufactured by the millions. Tuve assembled his team with characteristic directness, pulling specialists from universities, government laboratories, and private industry. Richard B. Roberts, a nuclear physicist and Tuve's colleague at Carnegie, became his deputy. Lloyd Berkner, an expert in radio engineering, tackled circuit design. Harry Diamond and Wilbur Hinman from the National Bureau of Standards brought expertise in radio-controlled systems. And in April 1942, a young physicist named James Van Allen joined the project, tasked with solving what many considered the single most impossible challenge: creating vacuum tubes that could survive artillery fire. Van Allen was 27 years old, a recent PhD from the University of Iowa with a fascination for instrument design. He approached the vacuum tube problem with systematic rigor, beginning by understanding exactly how conventional tubes failed. Standard vacuum tubes consisted of a glass envelope surrounding a tungsten filament and various metal grids and plates. When dropped from table height onto concrete, the glass shattered. When fired from even crude test cannons, the tubes exploded into powder. The problem was structural. Glass, by its nature, is brittle. It fractures under stress rather than bending. The internal components, particularly the hair-thin tungsten filament that heated to incandescence during operation, snapped under acceleration forces. Van Allen started experimenting with different glass formulations, testing variations in thickness, composition, and annealing techniques. He worked with Raytheon and Sylvania, companies that manufactured miniature tubes for hearing aids. These tubes were already smaller than standard radio tubes, roughly the size of a man's thumb rather than a light bulb, but they were designed for the gentle environment of sitting in someone's pocket, not the violence of gunfire. With engineers at Sylvania's Ipswich, Massachusetts facility, Van Allen began redesigning tubes from first principles. The glass envelopes were thickened in strategic locations and carefully annealed to relieve internal stresses. The filaments were shortened and given heavier cross-sections. The mounting system for internal components was completely reimagined, but the most ingenious solution came in how the tubes were supported inside the fuse body. Van Allen developed what the team called mousetrap springs, tiny mechanical devices that looked exactly like miniature mousetraps. These springs allowed the tube mount to flex and absorb shock during firing, while keeping the fragile tungsten filament taut during flight. The tubes were also potted in specially formulated wax inside the fuse body. This wax remained solid during storage, softened slightly to absorb shock during firing, then resolidified during flight to provide stable support. Testing these prototype tubes required creativity. Van Allen and his team built vertical test guns at rural sites near Washington. They would fire complete fuses straight up into the air, so the shells would fall back into soft earth, allowing recovery and examination. Each recovered fuse was carefully disassembled, and every component examined under microscopes to see what had broken and how. It was painstaking, methodical work. Fire a fuse, dig it out of the ground, examine every component, identify failure modes, redesign, fire again, through hundreds of test shots and thousands of design iterations. The success rate gradually climbed. By September 1941, fuses were surviving, firing about 50% of the time. Still far from ideal, but good enough that Tuve felt confident reporting to the Navy that a working proximity fuse was achievable. The vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in tropical heat. Navy shells might sit in storage for months or years before use. Engineers developed a revolutionary battery design, a reserve battery that kept the liquid electrolyte separate from the metal plates until the moment of firing. When the shell was fired, the violent acceleration shattered a small glass ampule containing the electrolyte. Centrifugal force then pushed the liquid outward against the metal plates, creating an electrical charge. This design gave the batteries virtually unlimited shelf life, while ensuring they activated reliably at the moment they were needed. The radio circuit itself employed elegant simplicity. A miniature oscillator generated radio waves at approximately 180 to 220 MHz. These waves radiated from a small antenna built into the fuse nose. When the waves struck a target, an aircraft's metal fuselage or even a human body, they reflected back to the fuse. Because both the shell and target were moving rapidly relative to each other, the reflected waves underwent a Doppler shift. The frequency changed in proportion to closing velocity. When this Doppler frequency reached a predetermined value, indicating the target was within lethal range, approximately 70 feet, an electronic circuit closed and fired a thyrotron tube. This tube acted as a switch, releasing electrical energy that triggered a conventional detonator, which in turn set off the main explosive charge in the shell. The entire system contained approximately 130 miniaturized electronic components, 5 rugged vacuum tubes, 1 reserve battery, a complete radio transmitter and receiver, multiple safety mechanisms, connections, resistors, capacitors, and inductors, all packed into a steel casing 8 inches long and weighing just over 2 pounds. By early 1942, Section T's research had outgrown the Department of Terrestrial Magnetism. The program was transferred to Johns Hopkins University, and a new facility was established. Tuve named it the Applied Physics Laboratory, or APL, and became its first director. The laboratory occupied a large building on Georgia Avenue in Silver Spring, Maryland, just outside Washington. By the end of the war, it would employ over 1,000 scientists, engineers, and technicians, all working on variations of the proximity fuse for different weapons and environments. On August 12, 1942, the light cruiser USS Cleveland conducted operational testing in Chesapeake Bay. 3 radio-controlled drone aircraft provided realistic targets. Cleveland's gun crews had been trained on the new ammunition, but remained skeptical. The drones maneuvered unpredictably, just as enemy aircraft would in combat. The gunners fired their first salvo. Proximity-fused shells exploded in a precise pattern around the lead drone, shredding it with fragments. The second drone fell moments later. The third attempted to evade but was caught by a perfectly timed airburst that destroyed it completely. 3 drones eliminated in less than 10 minutes. Navy observers watching from shore stood silent. They had just witnessed a fundamental change in naval air defense. Admiral Harold Bowen, who had championed the proximity fuse program from its inception, immediately recommended full-scale production. The Navy cancelled further scheduled tests. There was no need. The weapon worked better than anyone had predicted. 5 companies were selected to manufacture the Fuzes: Crosley Corporation in Cincinnati, which normally built radios and appliances; Radio Corporation of America; Eastman Kodak; General Electric; McQuay Norris. None had ever produced anything remotely similar to the proximity fuse. All would need to develop entirely new manufacturing techniques and quality control procedures. Production started slowly. By the end of 1942, factories were producing 500 fuses per day. But American industrial capacity was just beginning to mobilize. By late 1943, production had reached 40,000 fuses per day. More than 100 factories participated in some phase of production. Crosley alone would eventually produce 525,913 fuses, 24% of total wartime output. The company employed 10,000 workers operating around the clock, 7 days a week, achieving peak output of 16,500 fuzzes daily. Sylvania Electric Products in Ipswich, Massachusetts produced even more, manufacturing 5,683,032 fuses, while also producing 95% of all miniature vacuum tubes used across the entire proximity fuse program. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. The security classification surrounding the proximity fuse was extraordinary, second only to the Manhattan Project. Workers signed secrecy oaths and were searched when entering and leaving factories. They assembled components without being told what they were building. The fuse was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Even military personnel were initially told the fuses worked by measuring barometric pressure or some other non-radio mechanism. The deception was intentional. If the enemy discovered the fuse operated by radio, they might develop jamming techniques or other countermeasures. The first combat use came exactly as planned. On January 5, 1943, off Guadalcanal, where Red Cochrane's battery aboard USS Helena fired those 3 salvos at departing Japanese dive bombers, the news travelled through the Pacific Fleet like electricity. Word reached Admiral William Halsey's headquarters within hours, then Pearl Harbor, then Washington. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to fleet units throughout the Pacific. Combat results exceeded every prediction. Naval gunners who had struggled for months against Japanese air superiority suddenly possessed a weapon system that transformed near misses into kills. The statistics were remarkable. In 1943, the Navy fired 36,370 anti-aircraft rounds. Only 25% used proximity fuses. Yet those fuses accounted for 51% of house of it, all kills. The proximity-fused shells had a lethal fragment area of 3,000 square feet compared to 60 square feet for conventional shells. And because they exploded automatically at optimal range, there was no need for precise timing or range estimation. Point the guns at the target, fire, and let the fuse do the rest. Traditional time-fused shells required approximately 1,000 rounds to destroy a single aircraft. Proximity-fused shells needed only about 250. The weapon was 3 to 4 times more effective than conventional ammunition. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitcher commanding the fast carrier task forces, later recalled that proximity fuses knocked down enemy planes by the dozens. During the Battle of the Philippine Sea in June 1944, an engagement that became known as the Great Marianas Turkey Shoot, American task forces destroyed more than 600 Japanese aircraft in 2 days of fighting. Proximity-fused anti-aircraft fire accounted for a substantial portion of those kills. But perhaps the most dramatic demonstration came off Okinawa on May 11, 1945, during Operation Kikusui No. 6. 2 destroyers, USS Hadley and USS Evans, came under assault from approximately 150 Japanese aircraft, many loaded with explosives and intent on suicide runs. For nearly 90 minutes, the 2 destroyers and 4 supporting craft faced overwhelming odds. Hadley's gunners knocked down 23 enemy planes using proximity-fused ammunition before being hit by 3 kamikaze aircraft, 1 bomb, and 1 Oka rocket bomb. Evans accounted for additional aircraft before being struck 4 times. Both ships survived despite catastrophic damage. The after-action verdict on proximity-fused ammunition was unambiguous, indispensable. Throughout this entire period, the Pentagon maintained absolute restrictions on using proximity fuses over land. The risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. Intelligence analysts estimated that if Germany equipped its anti-aircraft guns with proximity fuses, Allied bomber losses could increase by 300%. The strategic air campaign against German industry might become impossible. British Bomber Command could be forced to abandon night operations. American daylight raids could be curtailed. So the Fuzes remained restricted to overwater use, where dud shells would sink beyond enemy reach. This restriction began to crack in June 1944, when Germany unleashed the Vosne flying bomb against London. The Vergeltungswaffe, or vengeance weapon, represented Hitler's attempt to break British morale through sustained bombardment of civilian areas. Launched from sites across the English Channel in occupied France, the V-1s approached at speeds of 400 miles per hour, flying at altitudes around 2,000 feet. Small, fast, and arriving without warning, they were extraordinarily difficult to intercept. British fighters struggled to catch them. Conventional anti-aircraft fire proved almost useless. From June through late August 1944, Germany launched over 9,000 V-1s against Britain. Initial defences could destroy only 17% of the flying bombs that entered the coastal gun belt. The situation was desperate. Prime Minister Winston Churchill personally authorized use of proximity fuzzes in anti-aircraft guns defending Britain. Modified fuses were rushed into production, specifically calibrated for the small, fast V1s. British and American anti-aircraft batteries along the southeast coast were equipped with proximity-fused ammunition, working in conjunction with advanced radar systems and gun-laying computers. The effect was dramatic. Within 4 weeks, the destruction rate climbed from 17% to 74%. During one day in late August, 82% of incoming V1s were shot down before reaching their targets. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining against Hitler's vengeance weapons. But the Vosne campaign demonstrated beyond doubt that the proximity fuse secret was partially compromised. Thousands of fuses were being fired over land. Dud shells were falling in fields and forests across southern England. The risk that had seemed so unacceptable in 1943 now had to be weighed against military necessity. When Germany redirected Vosne attacks toward Antwerp, the crucial Belgian port through which Allied supplies flowed to support operations in Western Europe, all hesitation vanished. Antwerp had to be protected regardless of security concerns. Lancaster bombers flew emergency missions from Cincinnati to Europe, transporting proximity fuses directly to anti-aircraft batteries. British and American gunners destroyed V1s by the hundreds, keeping Antwerp operational throughout the remainder of the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The calculation changed completely on the morning of December 16, 1944. That morning, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, the same ground where they had achieved breakthrough in 1940, aiming to split the Allied armies and recapture the vital port of Antwerp. The offensive took the Allies by complete surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. The weather was terrible, with heavy snow and thick clouds that grounded Allied air power. German commanders felt confident. Poor visibility made artillery observation nearly impossible. Traditional timed fuse airbursts required forward observers who could see where shells were landing and adjust fire accordingly. In the snow and fog of the Ardennes, such observation was impossible. They were catastrophically wrong. Colonel George Axelson commanded the 406th Artillery Group, positioned to support American forces near Monschau, Germany. On the morning of December 16, 1944, as German artillery began its preliminary barrage, Axelson faced an agonizing decision that would violate direct orders from the Pentagon. His ammunition dumps contained 200,000 proximity-fused artillery shells, code-named POSIT by Army Ordnance. These shells had arrived in Europe weeks earlier with explicit instructions: do not use over land, do not fire where duds might be recovered by the enemy. The restriction remained technically in force despite the emergency, unfolding across the Ardennes. Supreme Commander Dwight Eisenhower had not yet authorized their use in ground combat, but the 38th Cavalry Squadron, lightly armed reconnaissance troops dug in around Monschau, was being overrun by massed German infantry. They desperately needed artillery support. Axelson watched the situation deteriorating by the minute. His conventional shells were creating some casualties among the attackers, but German forces continued advancing. The timed fuse air bursts his gunners were attempting required precise range calculations that were impossible in the snow and poor visibility. Most shells were exploding too high or impacting the ground, their effectiveness drastically reduced. Axelson made his decision. The emergency trumped the restrictions. He ordered his gunners to load proximity-fused shells and fire for effect. Within minutes, 406th Artillery Group's batteries were sending POSIT rounds downrange toward the attacking Germans. Its effect on German forces was immediate and catastrophic. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. German soldiers, who had survived years of combat on the Eastern Front, who had endured the hell of Kursk and the grinding battles across Russia, had never experienced anything like it. Conventional artillery gave warning. You heard the shells approaching. You felt the ground shake as they impacted nearby. You learned to judge distance and trajectory. If you were in a foxhole or behind cover when a conventional shell landed, you had reasonable odds of survival. The fragments from a ground burst travelled outward and upward, leaving protected areas. Proximity-fused shells eliminated all of that battlefield wisdom. The shells made no sound as they approached due to their supersonic velocity. The first warning was the explosion overhead. The fragments rained down from above, penetrating foxholes, log-reinforced bunkers, and covered positions. Soldiers had no time to react, no way to take cover, no defensive measure that provided safety. Men pressed themselves flat against frozen earth and died anyway. The shrapnel came from everywhere at once. For 3 days, December 16th through 19th, proximity fuses remained officially forbidden, while American forces absorbed massive casualties across the Ardennes front. General Omar Bradley's headquarters received increasingly desperate reports from field commanders. German breakthrough attempts were succeeding across multiple sectors. Wehrmacht forces employed concentrated infantry tactics specifically designed to exploit the limitations of conventional artillery. They moved in mass formations during poor visibility when American observers couldn't effectively adjust fire. They used terrain that provided overhead cover from traditional airbursts. Eisenhower's fury during a conference call with Pentagon officials on December 19, 1944, became legendary among staff officers who witnessed it. The Supreme Allied Commander had spent 3 days watching German forces penetrate Allied lines deeper than any enemy advance since D-Day. His forces were dying while superior weapons sat unused in ammunition dumps because of bureaucratic security concerns. His language during that call was, by all accounts, volcanic. Within hours, all restrictions on proximity fuse use were permanently lifted for European operations. The authorization came through military channels on December 21st. Army code name POSIT, Navy code name VT, both referred to the same revolutionary weapon. And now American artillery batteries across the entire European theatre could fire them without restriction. The impact was immediate. Near Echternach, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River during daylight hours on December 24th. Patton had attended a demonstration of proximity-fused shells on December 16th, the same day the German offensive began. He had watched shells of various calibers exploding, approximately 20 feet above irregular ground with devastating effect. He had immediately recognized the tactical implications, but ordered the technology kept secret until it could be employed at a critical moment. Christmas Eve, 1944, provided that moment. Patton's artillery battalions fired concentrated barrages of proximity-fused shells at the German forces attempting the river crossing. The shells exploded precisely above the exposed troops with methodical regularity. By actual body count, 702 German soldiers were killed in a single engagement. Eliminated in minutes. Patton later wrote to the War Department describing the action. The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first. The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Colonel Otto Skorzeni's Panzer Brigade 150, part of the elaborate German deception operation called Operation Greif, attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effectiveness. The air burst so unnerved the attackers that some charged directly into American positions, seeking any shelter from the overhead explosions. The assault was repelled by afternoon. German prisoners of war, interviewed by American intelligence officers, captured the psychological impact with stark clarity. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. The officer's assessment was technically accurate. By late 1944, American factories were producing 70,000 proximity fuses per day. That represented nearly 3 billion individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world. Another prisoner, a Luftwaffe engineer with technical training, focused his analysis on air defense implications. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt. But he immediately added a crucial caveat: Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate and personal revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match, by an enemy whose industrial power exceeded anything they had imagined possible. The Battle of the Bulge demonstrated how American tactical doctrine had evolved to maximize the fuse's effectiveness. Forward observers no longer needed visual confirmation to call down devastating fire. Artillery batteries laid barrage patterns covering entire areas. The proximity fuses meant that every shell was an effective airburst, regardless of terrain or visibility. Shells exploded above forests, penetrating tree cover, above snow-covered fields, above villages and towns. The consistency was terrifying. German tactical doctrine, developed over years of warfare on multiple fronts, had to be completely rewritten. Traditional defensive positions became death traps. Foxholes offered no protection. Log bunkers were penetrated from above. Moving in the open during artillery fire was obviously suicide, but remaining stationary in prepared positions provided no safety either. The Germans tried to adapt by dispersing more widely and staying constantly on the move, but dispersion reduced combat effectiveness and made coordinated operations difficult. Wehrmacht doctrine had evolved around concentrated formations that could mass firepower and maintain unit cohesion. Dispersing to counter proximity fuses weakened overall capability, even as it reduced casualties. More ominous for German commanders, some units began exhibiting what American intelligence reports termed artillery shock syndrome, a psychological condition specifically triggered by the helplessness of facing proximity-fused fire. Soldiers who had endured years of combat, who had never broken under conventional artillery bombardment, began refusing orders to advance into areas under American artillery coverage. Officers reported discipline problems. Men would not leave protected positions even under direct orders. Some units experienced what approached mutinous behavior as soldiers prioritized survival over military objectives. German commanders offered rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. Technical intelligence teams were specifically tasked with recovering unexploded American shells. Wehrmacht engineers desperately wanted to understand how the fuses worked, but even when they recovered intact examples, they failed to comprehend what they were examining. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, German engineers never fully grasped that miniature radio transmitters were inside every shell. Some German technical reports described the captured fuses as containing complex clockwork mechanisms or barometric sensors. Others speculated about magnetic detection systems. The actual radio transmitter and receiver circuits, visible under the Fuze's nose cap, were examined but not understood. The vacuum tubes seemed impossibly small and impossibly rugged. German engineers knew that vacuum tubes shattered under far less stress than artillery firing imposed. Therefore, what they were looking at could not be vacuum tubes. It must be something else, some elaborate deception perhaps. Dummy components designed to mislead German analysis. This fundamental misunderstanding meant that German countermeasures research pursued entirely wrong directions. Engineers designed jamming systems for frequencies the Fuzes didn't use. They developed tactics against weapons they didn't understand. They allocated resources to solutions that addressed non-existent problems. Meanwhile, American artillery continued killing German soldiers by the thousands, with a weapon whose basic operating principle remained incomprehensible to Wehrmacht technical intelligence. By January 1945, as Allied forces began advancing toward the Rhine River and into Germany itself, proximity-fused anti-aircraft fire had also achieved devastating effectiveness against the Luftwaffe. German pilots reported shells that seemed to explode whenever aircraft approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became nearly impossible to penetrate. From January through March 1945, proximity-fused anti-aircraft shells brought down more than 1,000 German aircraft. Luftwaffe bomber formations attempting night raids found themselves flying into walls of precisely timed explosions. Fighter bomber units assigned to ground attack missions faced anti-aircraft defenses that achieved hit rates previously considered impossible. The psychological effect on German pilots matched what ground troops experienced. Flying through proximity-fused anti-aircraft fire created a specific type of terror. You could see the black puffs of explosions tracking your aircraft. You could maneuver violently, diving and climbing and banking, and the explosions followed. They anticipated your movements. They boxed you in. Traditional anti-aircraft fire created patterns you could evade. You learned to recognize the approach of timed fuse barrages and adjust your flight path. Proximity-fused fire eliminated that battlefield learning. The shells detected your presence and detonated at optimal range. Your only option was to avoid the engagement zone entirely, which meant abandoning the mission. Ground combat intensified as Allied forces pushed deeper into Germany. During the Rhine crossing operations in March 1945, American artillery fired tens of thousands of proximity-fused shells, creating concentrated destruction that German defenders were unable to resist effectively. The shells proved particularly devastating in urban warfare. Fuses could be set to detonate at rooftop level, showering entire city blocks with shrapnel and making defensive positions untenable. German forces attempting to hold towns and cities found themselves unable to survive in buildings that conventional artillery would have left partially intact. General Eisenhower, writing his post-war memoir, acknowledged the contribution of the proximity fuse in stark terms. He stated that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. The counterfactual scenario was genuinely chilling. German anti-aircraft defenses, equipped with proximity fuses, might have made the D-Day landings unsustainable. Landing craft approaching Normandy beaches would have faced artillery fire that didn't need to score direct hits. Air bursts over the beaches would have created casualty rates that could have halted the invasion. German artillery using proximity fuses during the Normandy campaign could have inflicted losses that stopped the Allied breakout from the beachhead. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Koenig acoustic fuse used a mechanical tone filter connected to a resonating reed switch that would trigger on specific engine frequencies. Rheinmetall-Borsig developed an electrostatic fuse using capacitive detection to sense the approach of charged aircraft. There were optical fuses using photoelectric cells, magnetic fuses using induction coils, and experimental radio fuses conceptually similar to the American design. but none had advanced beyond limited testing. When Rheinmetall resumed proximity fuse research in 1944, under direct orders from Hitler's armaments ministry, engineers developed hundreds of working prototypes. Test firings achieved reasonable success rates. The technology was feasible, but by late 1944, Germany lacked the industrial capacity to establish mass production. Even if production facilities could have been built, the resources required would have competed directly with production of tanks, aircraft, ammunition, and fuel. Every factory worker assigned to proximity fuse production was a worker not building Panther tanks or Messerschmitt fighters. Every kilogram of copper wire used in fuse electronics was copper not available for other weapons. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget, over $1 billion 1940s dollars, approximately $15 billion in modern purchasing power. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, establishing quality control systems, and maintaining absolute operational security around the entire program. The production statistics were genuinely staggering. At peak output, American factories produced 70,000 fuses per day. Each fuse contained 130 individual components manufactured to precise specifications. 5 miniature vacuum tubes, 1 reserve battery, dozens of resistors, capacitors, and inductors, radio transmitter and receiver circuits, safety mechanisms, detonator assemblies, all packed into a space smaller than a coffee cup and assembled by hand under microscopic examination. The cost per fuse fell dramatically as production expanded. In 1942, early production units cost $732 each. A single proximity fused shell cost more than a soldier's monthly pay. By 1945, mass production techniques and economies of scale had reduced the cost to $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, improved efficiency, and the sheer volume of production. At $18 per fuse, the weapon remained expensive compared to conventional ammunition, but the increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness represented obvious value. The secrecy remained absolute until the war's end. Production workers at different factories did not know other facilities were building identical components. Suppliers manufactured parts without understanding their purpose. The security classification stayed in force until September 1945, when Germany and Japan had both surrendered, and the proximity fuse was finally revealed to the public. News coverage described it as one of the war's most important technological developments, ranking alongside radar and the atomic bomb in strategic impact. For German prisoners of war held in Britain, who had witnessed anti-aircraft guns defending against Vosne attacks, the revelation of what they had faced came with profound psychological impact. They could now see the complete picture. The same technology that had devastated their forces in the Ardennes was protecting British cities from German vengeance weapons. The Americans had developed a weapon that German engineers had concluded was impossible. They had manufactured it by the millions. They had deployed it globally across both theatres of war, and they had kept it secret until revealing it no longer mattered. The technological legacy of the proximity fuse extended far beyond its immediate military applications. The miniaturization techniques developed for rugged vacuum tubes influenced the entire electronics industry. Engineers who had learned to make components survive 20,000 Gs of acceleration and 25,000 RPM of spin, transferred that knowledge to civilian applications. The quality control methods became standard practice in manufacturing. Statistical process control, automated testing procedures, and supply chain management systems developed for fuse production shaped post-war American industry. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. Thousands of workers, many of them women with no previous technical experience, learned to assemble intricate electronic devices under microscopes. They maintained production quality standards that would have been considered impossible in pre-war manufacturing. This expansion of the technical workforce created an industrial base that supported America's post-war technological dominance. James Van Allen, the physicist who developed rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. When the Explorer 1 satellite launched in 1958, its instruments drew directly on proximity fuse technology. The Geiger countertubes that detected the radiation belts, later named for Van Allen, used design principles developed for artillery fuses. Making electronics survive artillery, acceleration helped make electronics that could survive rocket launches into space. The knowledge gained from one seemingly impossible task enabled the next. The space program, the development of computers, and the transistor revolution all drew on knowledge and techniques developed during the proximity fuse program. Scientists and engineers who worked on the fuse went on to distinguished careers. Merle Tuve continued leading scientific research at the Carnegie Institution. Dozens of Section T veterans joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering. The intellectual capital developed during the proximity fuse program helped establish American leadership in electronics and technology throughout the second half of the 20th century. The industrial infrastructure created for fuse production found new uses after the war. Factories that had manufactured vacuum tubes converted to producing television tubes and consumer electronics. Workers trained in precision assembly became the workforce for the emerging electronics industry. Supply chains established for fuse components supported the growth of consumer electronics markets. The transition from military to civilian production happened smoothly because the skills and infrastructure were transferable. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix air-to-air missile, the Standard missile family, and the Patriot surface-to-air missile all employ proximity fuses based on the same fundamental concept developed in 1942. Today's fuzzes use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys. They operate in jamming environments. They coordinate with other weapons in networked defensive systems. But the core principle remains unchanged. Detect the target using electromagnetic radiation. Calculate the optimal detonation point. Trigger the warhead for maximum effect. The story of the proximity fuse is ultimately about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons that captured imaginations. Jet aircraft that flew faster than anything the Allies possessed. V-2 ballistic missiles that reached the edge of space. These were impressive technological achievements that demonstrated German engineering brilliance. But they came too late and in too few numbers to affect the war's outcome. Germany built approximately 1,000 Me 262 jet fighters, impressive aircraft that achieved local air superiority wherever they appeared. But 1,000 jets could not reverse the strategic situation when Allied air forces numbered in the tens of thousands. America invested in technologies that could be mass-produced immediately. Proximity fuzzes, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability. The result was a weapon available in overwhelming numbers when needed. 22 million proximity fuzzes produced during the war. Not laboratory prototypes or limited production weapons, but fully operational fuzzes deployed globally and used in combat by multiple services across both theaters. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority, wonder weapons that would change the strategic balance through technological breakthrough. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. In the final accounting, The proximity fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable. It perfectly exemplified how America fought and won the war, by solving impossible problems through application of extraordinary resources, brilliant engineering, and an industrial base that could produce technological miracles by the millions. The German soldiers who faced proximity-fused fire understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. They had fought an enemy who could allocate billions of dollars to develop a single weapon system, who could mobilize over 100 factories to manufacture it, who could train tens of thousands of workers to assemble components so complex that German engineers examining captured examples couldn't understand how they functioned, who could ship 22 million fuses to combat theaters around the world while simultaneously producing aircraft, ships, tanks, and conventional ammunition in quantities that exceeded Germany's entire industrial output. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.